Hi, this is Chemical Kim again, and we're going to work on another activity from Unit 7, which is the practice problems on percent and theoretical yield. So I thought I would do a couple of them with you, and then you can try. So let's look at number 73 in the practice problems. So open up Unit 7 practice problems, and we'll start with number 73. You also want to have a calculator out in front of you. You would be most helpful always to have the periodic table. And if it does help too, on that EMD app, periodic table app, you can go to the menu option and have that molar mass calculator, which will help us finding the molar masses of some of these values that we're going to be needing in the calculation. So let's look at number 73. First, we see that the equation is not balanced, and yet I haven't tackled the stoichiometry of it, but I do always want to balance my equation. Hopefully you're at a place where you're very comfortable with balancing equations. To have this one balanced in particular, I need to put a 2 in front of the HCl and a 2 in front of the NaCl, and that is balanced. And I like to put those coefficient ones. So this question provides to me 5.00 grams of my start material, sodium carbonate. It also indicates that an experiment was done. And I know that because it shows this actual yield. And the actual yield is not determined by calculation, it's determined by actually doing the experiment. So I'm going to use that number to tackle letter B on this question. What I highlighted first is what I'll be using to tackle letter A, and that is to calculate the theoretical amount. The theoretical amount is the amount that you determines produced by calculation, by doing a stoichiometric calculation. So I'm going to be looking at doing stoichiometry between the sodium carbonate and the carbon dioxide. So just like I've done in my stoichiometry videos, I'm going to do those 3 steps of stoichiometry because it's a gram to gram conversion. So I'm going to start with that, 5.00 grams of the sodium carbonate of the Na2CO3. And my first step of stoichiometry, and I'll kind of hopefully fit all 3 steps here. My first step of stoichiometry is to use the molar mass. And as you see, I already found that molar mass by using the molar mass calculator, or if you wanted to, you could add up the atomic masses of those in the formula. So that's 105.99. I'm going to put that down here at the bottom, and that will be grams of Na2CO3. I like to label everything, and because it's molar mass, it's going to be over just 1 mole. Okay, and that's not because there's a 1 coefficient in the balanced equation. You always put it with 1 mole with the molar mass. Okay, so be careful about that. We're not looking at the balanced equation for this first step. I'll put a 1 underneath that first number just so you can see that fraction. Then my second step, and I'll change colors here just to kind of indicate and let you know this is where I'm going to do what we call the bridge step, which is using our balanced equation. And I see the ratio of CO2 to sodium carbonate, the Na2CO3, is a 2-to-1 ratio. To calculate that, I would be putting the 2 mole CO2 on top and the 1 mole Na2CO3 on the bottom. So what I just did is bridge using that balanced equation, that one. Oh wait, I made a mistake here, didn't I? Let me make that correction. It's not a 2 in front of the in front of the CO2, it's just a 1. So there you go. Can recheck and double check. So those coefficients are just 1, so it's actually just a 1-to-1 ratio from my balanced equation. So that's my bridge. Okay, so I'm bridging, and as I've done in the past with some of my past lessons, I've shown that I like to cancel units as I set up the problem. Okay, so then my last step is to use the molar mass of CO2 because that's the theoretical yield I'm trying to determine by calculation. The molar mass of CO2 is determined by adding up the atomic masses from the periodic table, and I determined that to be the 44.01, and that is grams CO2. And again, because it's molar mass, I'm going to put it as 1 mole CO2. So right there is the entire calculation that I'm going to do to determine the theoretical yield. So to put these numbers into my calculator, I'm going to take my 5.00 and then divided by 1, of course, gives me the same number. Then I'm going to multiply that times 1, and again, that will give me the same number. Now I'll hit divide 105.99, and that will give me the moles of Na2CO3. Now, of course, the bridge step is a 1-to-1 ratio, so it is also equal to the moles of CO2. So my last thing to calculate is just hit times 44.01, and I get a theoretical yield. So for letter A, my theoretical yield by calculation is 2.08 grams. Okay? So with that, I can move on to letter B, and letter B is determining the percent yield. This really does determine this percent yield on how well the experiment was performed. So the calculation for percent yield looks like this. To do percent yield, we're going to take the actual yield divided by the theoretical yield, and then we'll multiply it by 100. The actual yield, like I said, was determined by experiment. So if you did the experiment, you would obtain that actual yield. But the problem lets us know that the actual yield was 1.50. So I'm going to use that to determine the percent yield. I'll take my 1.50 grams of CO2. I'll divide that by the theoretical, which I determined by calculation to be the 2.08 grams. I'll multiply that by 100, and that will give me my percent yield. I can already tell that I didn't get a good, or this particular data is not the best because it doesn't match 2.08, but let's see what its actual calculation is. So 1.50 divided by 2.08 times 100, and I end up with 72.1%. And I'll carry it to that significant figure. So that's a percent yield calculation. Very simple. If you would like to, continue and try this one, we can take a look at it together, and maybe we'll see if this will kind of move us in the direction of figuring out percent yield and theoretical yield. But if you want to pause the video, try it before you see it, you're welcome to do that as well. So let's take a look at this one. Right away, before I even check the question, I always like to see if my equation's balanced. And I do see, in this case, if I have CH4 plus Cl2, I already see that my Cl's are not balanced, okay? My H's are not balanced, so, it doesn't matter really which one you want to tackle. I'm going to tackle the H's just because my Cl is by itself on the reactant side, and usually I like to do whatever's by itself at the end. So I'm putting a 4 in for the HCl to balance my hydrogens, and then that gives me 8 chlorines on the reactant or on the product side, because you notice that 4 right there plus the 4 chlorines. So I want to then put a 4 chlorine on the reactant side, 1 CH4 plus 4 Cl2s, and that's going to give me 1 CCl4 plus 4 HCl. So that should give me my balanced equation. Looking at the question, because this is a percent yield calculation, I have to have the actual yield by experiment right there. And that is what I mentioned before. That's the actual by experiment. Okay. And then I want to figure out the percent yield, but the start material that I'm given is 1.04 moles CH4. It's not grams like what we saw in the other question. But if you remember, we've worked on stoichiometry, and hopefully you've been working on the stoichiometry problem. This isn't too hard to handle because we're not starting with a gram quantity, we're starting with a mole quantity of a reactant. We can still do stoichiometry, but really only doing 2 steps of the stoichiometry. So let's do those. So I'm going to start with my 1.00 moles of CH4, and I'm going to bridge that to Cl2. So what I like to do, CCl4. What I like to do is highlight in my equation the 2 materials that I'm bridging between. And that lets me know I'm going to focus on those 2 in the stoichiometry. Okay. And the reason I knew CCl4 is because that's the actual yield value that I have to compare to. So I need a gram quantity of the CCl4. So I'm going to do that bridge step, which just like in the previous question, not that this always happens, but in the previous example I just did, I have another 1-to-1 ratio. And again, that's just from that balanced equation. 1 mole CH4 to 1 mole Cl4. And then my last step is to use the molar masses to calculate, or atomic masses, to calculate the molar mass of CCl4. And I'll take you through the longhand steps of that just to, review molar mass calculation. So 12.01 for my chlorine, or for my carbon, and then my chlorine is 35.45, but I have to multiply that 35.45 times 4 because it's CCl4, okay? And I get a molar mass of 153.81. Just as a reminder, if you wanted to use that molar mass calculator, it would look like this. And I would want to lowercase my L, carbon, and chlorine, and then 4, 153.823. So pretty close, 153.81 I'll use with my calculation just because that's how I put it together with rounding. And we're pretty close to the molar mass calculator. So 153.81 grams of CCl4 over 1 mole of CCl4. So that's my molar mass step. So I really did just start with the bridge step in stoichiometry, and then I did the molar mass step. So to calculate this, I'm going to start with my 1.00. Easy calculation, times 1 divided by 1 is 1. And then I'm just basically multiplying times the 153.81. I didn't really even need my calculator, did I? All I did was multiply 1 times that final answer. So anyway, my theoretical mass, I end up getting 153.81 grams. So that's my theoretical, okay? And my theoretical yield is what I'll call that. To do the percent yield, we're going to do the actual divided by the theoretical. The actual was 96.8 grams. I'm going to divide that by the 153.81 grams, multiply that times 100. So 96.8 divided by 153.81 times 100, so times 100, and I get 62.9% yield. Okay, not exactly the best yield, but again, that's your percent yield calculation. So I hope this helps, and I hope you can maybe continue and try number 75. When you tackle number 75, you should end up with a 91.2% for the answer. And just to kind of talk you through it, the equation's already balanced, and it does look a bit complex with a lot of wording. It indicates toluene is oxidized, so here's our toluene, if that helps, by air, and the oxygen in the air is what's doing the oxidizing. Under controlled conditions to benzoic acid, which is used to prepare food preservatives, sodium benzoate. What is the yield of a reaction in which 1.00 grams of toluene is converted to 1.21 grams of benzoic acid? So if this helps, I'll highlight benzoic acid and benzoic acid. So you will start for the theoretical yield, okay? You'll start with your given 1.00 grams of toluene, which is C6H5CH3, and you'll do those 3 steps of stoichiometry to figure out a produced mass by calculation of that benzoic acid, which is C6H5CO2H. Okay, so that's your theoretical. And then to do the percent yield, you would take that theoretical, or not the theoretical, you're going to use it, but first we're going to use the actual yield, which it indicates is that 1.21 grams, 1.21 grams, and you notice in parentheses it does indicate that actual. And then we'll divide that by the theoretical that we obtained in the calculation times 100. And again, you should get that 91.2, but you give it a try. See what you get. Okay, so good luck. Hope this helps.